Okay, we study X22, properties of waves. Number one, find the fourth statement regarding trigonometric identities. In here, we have same style of sinusoidal function, cosine, cosine, sine, sine, e to the I theta, e to the I theta. The difference is the phase difference between the two terms that are being added. And if we have a phase difference, beta, the overall, it is absolutely factorized. The original sinusoidal function multiplied by 2 times the cosine half of this phase difference. It is a very, very important. You have to remember absolutely. Find the false statement regarding the interference of two monochromatic waves. Monochromatic, the wavelength is the same, the frequency is the same, of equal wavelengths, of equal amplitude A, and phase difference phi. So we have a geometric interpretation of the two vectors having angular difference phi. In that case, we have a rhombus of four sides being the same, then diagonal of this rhombus is 2 times A. This is the length of one side, 2 times A, half of cosine. So 2 times means that this is double. So this is half of cosine, A. This is 1/2 of phi, and this length is cosine, A cosine, 1/2 of phi. And this length, they are the same. This one also has cosine half of phi. That's the reason why the total length of the diameter, this is 2 times A cosine half of phi. This is also true when we introduce the complex number with the same amplitude. Amplitude means the absolute value of a complex number, that is modulus, that is called modulus. And we have a phase measured from the real axis. In that case, two complex numbers of equal magnitude are being added. If they have a phase difference by phi, then the result of the sum is 2 times A. A is the absolute value of the complex number, and cosine 1/2 of phi. That is exactly the same for the two-dimensional Euclidean space and this complex plane. And we have two extreme style of resultant amplitude that is fully destructive. That means when cosine 1/2 of phi is exactly 0. It is called fully constructive if this one is plus minus 1. This is true when we have phi to be even power, an even multiple of pi. And this is an odd multiple of pi. Pi plus minus pi plus minus 3 pi, and so on. And this is 0, 2 pi, and 4 pi, and so on. So when this one happens, the amplitude is doubled because it is plus minus 1, plus minus 2a, absolute value is 2a. So amplitude is double. In this case, amplitude disappears. This one becomes a 0. So amplitude disappears. We say this is fully destructive interference. This one is a fully constructive interference. You can solve this problem with this logic. Find the standing wave. Standing wave happens when two waves of equal wavelengths and opposite motion. The propagation direction is absolutely opposite. In that case, you will find the standing wave. Here, x and y. Kx minus omega t. This one has a velocity along the x-axis. So E1, V, something like that. And what is the velocity? We have, this is 2 pi lambda, 2 pi period. Omega is 2 pi over period. K is 2 pi over lambda t. So this one, this V, can be obtained in this way, or K over omega over K, something like that. So from this, we infer the direction of the propagation. So this one propagates along the x-axis with a V. This one also propagates with V. However, the direction is along the y-axis. So to make a standing wave, we need the two waves move in opposite direction. So this one is along the x-axis and this one is moving along the y-axis. So it's not. In here, we have kx, that's fine. However, we have minus omega t and minus omega t. So both of them are moving with the v along the same direction. They are parallel. So they just add up. Therefore, it does not contribute to the standing wave. Standing wave should be made when they collide in opposite direction. They are in opposite direction? No. It is along the x-axis and along the z-axis. So that is not, they are not making a head-on collision. The only thing is D. This one is propagating along the y-axis. Y-axis, that's fine, but with opposite velocity. So this one generates a standing wave. Number 4. Find false statement regarding a standing wave. This is a standing wave. We call this one, these points. It does not oscillate at all. They are all fixed, just like what we find when we look at the vibrating string. In fundamental mode, it oscillates. Every part oscillates, but their amplitudes are different. These two endpoints are fixed, and the middle point has the maximum amplitude. So this kind of wave is called the standing wave. We call this fixed point that does not oscillate, that is node, and the maximum oscillation appears at the antinode. Longitudinal coordinates of nodes. This is a longitudinal direction. This is longitudinal and this is a transverse direction. Longitudinal coordinates of nodes and antinodes are invariant. Yes, this position doesn't change. as time goes by. So this position, they are fixed, invariant. Okay. An antinode does not make an oscillation at all times. Antinode. This is antinode. It is a wrong. So I should correct this one. And a node. Wait a second. It should be a node does not make an oscillation at all times. A node does not make an oscillation. Antinode is of a maximum oscillation. So it is wrong. So it is correct. The distance between any two nearest nodes is the half wavelength of each partial wave. The actual wavelength is this amount. This is the wavelength of the actual wave. However, this node, nearest nodes, and nearest antinodes appears 1/2 of the wavelength. This is 1/2 of the wavelength. Okay. Number 5. Find the false statement regarding the resultant wave. We have a function. This one is called even function. Even function. If I replace the sign, the result is the same. Examples of even function is a y equals x squared or cosine. They are even functions. Okay. And I use this even function. I substitute two waves. They are moving in opposite direction, right? This is going forward with plus v, and this one is moving backward with velocity minus v along the x-axis. Remember, I have put the negative sign on it. Okay, why don't we calculate psi t0? Substitute f of x, t equals to 0 minus f of x. Not t equals 0, x equals 0, sorry. X equals 0. So 0 minus 0, but I told you it is an even function, so it is a Vt minus Vt. So they cancel, it is 0. This one shows that x equals 0 does not oscillate at all time. That means this is something like antinode. Node, not antinode. Node does not oscillate. Because it is always 0, this is a node of a standing wave. That's fine. This one travels with the velocity plus v along the x-axis. That's correct. This one travels with the velocity minus v. That's correct. Still, we are making use of an even function. We have a plot. This blue wave travels along the x-axis. This one is E1 hat. And this green wave, we have a plus sign on it. Therefore, its motion is backward. VE1 minus, and this is VE1 plus. Okay, they are making a head-on collision. We expect that the resultant wave will be a standing wave. We are using the same style of superposition of two waves. Therefore, as we have obtained already, there is a node here at x equals 0. It does not oscillate at all or at all time. Okay, two waves, this one, and this one, cancel at x equals 0. They are out of phase. We need to remember what is out of phase. Fully destructive, we call it is out of phase. Fully constructive, we say they are in phase. They are added up to make the amplitude twice, and we say it is in phase, and they cancel exactly, then we call out of phase. When the two waves completely overlap, okay, it goes forward and it goes backward, then we have the two waves in opposite direction. Some of them will be 0 exactly. The resultant wave disappears due to the fully destructive interference. That's right. The resultant wave is an odd function of x at any t. At any t. Let's see. So psi tx equals this one, fx minus vt minus fx plus vt. And in order to find whether this function is even or odd, I need to replace this x with minus x. So psi t minus x equals f of minus x minus v minus minus x plus v t. That's this. That's this. Okay, I can pull this negative sign out. Because this function f is an even function, I can remove this negative sign on it. So this one is identical to this. In a similar manner, I can pull out the negative sign, write it in such a way. So this one disappears. All right. However, this is this and this is this. They are A minus B style and the B minus A style. So this wave function at minus x is identical to tx, except that we have negative sign on it. That means if I substitute minus x for x, I have negative sign. That means this function is an odd function of x at any t. That's correct. If we look at the region either x positive or negative, then the propagation of a wave reveals the reflection of a wave at a fixed end. Okay, just as time goes by at t equals 0, these two resultant wave completely disappears, and then after that, this green one goes backward in this manner, and this blue wave go further to the right. So if I just remove this part and look at the left part only, then this wave is coming in, and there is a point, fixed point, where the wave is always the zero, and then finally something like when after that reflected wave is flipping the direction. So it was above the horizontal axis, but after the reflection, this is below the horizontal axis. This is a realization of reflection of a wave at a fixed end. Although we do not carry out the experiment with a fixed end, this is effectively summation of these two waves that are making a head-on collision reveals the mechanism of a reflected wave around the fixed end. Okay, so after reflection, reflected wave changes its phase. For example, this one and this one, they are completely out of phase by pi, right? Just like that. Find a false statement regarding the resultant wave. Now we are using this one, even function, but the sum. We can see the resultant wave at x equals 0. At x equals 0, if I substitute 0, we know it is an even function. It is a doubled. Aha, it is a completely constructive interference. The amplitude is doubled. At t equals 0, the resultant wave is, if I substitute t equals 0, again, I have the twice the original amplitude. X equals 0 is an antinode of a standing wave. We know maximum amplitude is an antinode. So unlike the case of subtracted case, that is a node, in this case, we have an antinode at x equals 0. It is just like wavy flag. Wavy flag am I right? In here, this is a free end. In here, there's a fixed end. This wavy flag reflects at this point. Immediately, the direction becomes opposite. When the wave comes in this way, when it reflects, it oscillates in opposite direction. And at free end, the oscillation is doubled. Here is a node, and here is antinode. So after reflection, though it is magnified by twice at the end point, so it usually won't fold up, okay, because it oscillates faster along the same direction. This is an anti-node, and this is node. All right. Find the false statement regarding the following figure regarding harmonics. So in the lowest line frequencies, we can make an approximation as a multiple of a fundamental frequency. However, as n increases, the Pythagoras formula breaks down. So the correct way of formulating the higher order frequencies of the harmonics is this one, as we learned in the previous class. So this R runs from 1 to n. Here we made an approximation. The string consists of n tiny massive bees, and there are kinds of distinct frequencies called harmonic, and the number of frequencies available is exactly the same as the number of bees consisting the string. Okay. When we increase this number, when r is very small, then sine theta can be approximated similarly to theta. In that case, this one follows the multiple rule. However, as n goes to a very large infinity, for example, then it becomes n over 2 n plus 1 pi. So for large n, it is just half of pi. You know, sine half of pi is just 1. So it does not grow up to a large number. The sine function does not allow a strict increase of the frequency. So this one is wrong as n goes to a very large. This is the correct formula. Okay. Please remember this formula. This tension divided by density. Density is a mass over length of the string. This one determines the speed. The fundamental frequency, string length, this is half of the wavelength. 1/2 of wavelength is L, so wavelength is 2 times the length of the string, and this amount determines the speed of a wave on a massive string under the tension tau. Next, we consider the propagating sound wave. To find a false statement regarding the following figure of air in a cylindrical open tube that forms a steady state. A steady state means everything is independent of time. The change in pressure makes the air molecules vibrate. However, when the steady state is achieved, the change in the density with respect to time must always vanish. So this continuity equation becomes very simple. That is, a divergence J equals 0 because the density doesn't change at all with respect to time. And air molecule flow, mass flow, that can be expressed as a current density, that is a density multiplied the velocity on the right lid of this cylindrical partition. And the same current flow at x plus dx, where dx is the tiny amount of the thickness of this cylindrical partition. Then the change in the current on the left side and right side, this subtraction, must vanish because of the continuity equation. We know that this side does not allow the flow of mass because it's a fixed tube. There is no way of transmitting mass in this side, so it is completely fixed. As a result, the current flow comes in to this side and comes out this side. They must be the same. We know the current density is a product density and velocity. So density multiplied the velocity on this side is exactly the same as the one on this side. That is a rho prime, v prime, something like that. As a result, rho v is this current density that is a constant. If it is a constant, it's a differential. Must be 0. This one results in a simple relationship among the velocity of the mass flow, and this A is a cross-sectional area. If we multiply the cross-sectional area and oscillating time, both sides, this one is identical to this. Finally, this one is a cross-sectional area, and VDT is just the thickness of this cylindrical container. That is cross-sectional area times thickness, that is a volume. In a similar manner, this one in the numerator is a change in volume. And because this one makes the change in the density in every point in space, when the velocity increases, because of this positive sign, when we move this one to the right hand side, we have negative sign on it. So change in velocity on this side and this side divided by its own velocity is the same as negative of the change in the density of air molecules this side and this side. Again, steady state, time independent. Because of this continuity equation is simplified. And when the divergence equals 0, divergence theorem states that this integrand is 0, so surface integral is also 0. This surface integral is 0, and there is no integral on this side. The only allowed value is this side and this side. And the sum of these two must cancel because divergence must vanish. So that is the result of continuity equation. 10. Find a false statement regarding the sound propagation in the air. In an ideal fluid, the pressure change at a certain point immediately transferred to everywhere in the fluid, according to Pascal's principle. That's correct. If you apply delta pressure at this point and anywhere else, delta P is transferred immediately without delay. An ideal fluid does not change its volume under any compressive stress. Yes, ideal fluid is incompressible. However, air is compressible, so air is not an ideal fluid. Hence, it has a zero strain against compression stress. Strain, change, there is no change. Bulk modulus of an ideal fluid is infinite because the stress is a finite over strain. Strain is a change. There is no change. Substitute the zero in the denominator, it goes to infinity. Air is not an ideal fluid because it is compressible, yes, has a finite strength. It is not zero, but finite. So bulk modulus of air is finite. Bulk modulus is just like tau over rho determines the speed of a wave along a string. It is very similar to, say, bulk modulus over density. This is the length density, mass density per unit length, this mass density per volume. This bulk modulus determines the speed of sound. Yes, if it is a zero, strain is a zero for ideal fluid. In that case, this V goes to infinity. That is an unphysical. 11. Find a false statement regarding a constant current density independently of T and X. J equals constant. Constant is a simpler case. In general, divergence J equals 0, but if I substitute a constant J, it is also satisfying the divergence is 0. So again, I can make use of continuity equation. I told you J current density is rho times V, right? So this differential, this current density doesn't change because J is constant in this problem. And we have thickness dx. Here we have J of x, and this side we have J of x plus dx. The change in this two current, should be expressed as a differential of dx. We know time dependence disappears as steady state, so we have a single variable problem with respect to x, all right? And this one results from this result because J is constant and J is a product of rho and V, and this one is identical to this relation. And again, what I have done with this relationship by multiplying the cross-sectional area and time delay from this and this side because of the velocity of the wave, we have all three factors are the same except for this sign. All right. Finally, we have reached the point the velocity of sound is interpreted as a change in pressure and the ratio of the change in pressure and density coming from this relation. And then finally, this dV is a kind of strain, and dp is a kind of stress, and we have a ratio of stress over strain that becomes, except for rho, this one becomes the bulk modulus, stress over strain style. Okay, these are the straightforward calculation. The force, now we consider the force applied to the left side of the cylinder, and we consider the force on the right side of the cylinder. The force is the pressure multiplied by the cross-sectional area. So F net is the sum of this force on the left side that is applied to this direction, and this one is the force applied to the right side, so that is applied to the left direction. That's the reason why we have a negative sign on it. So sum of these two forces gives the net force that can be computed as a function of x. And as I have already explained, this steady state pressure can be expressed as this kind of form. Just change in x can be considered as a change in x can be considered as a partial derivative with respect to x and multiplied by dx, something like that. So after subtraction, after this sum becomes a subtraction, difference between these two, because the direction of force is to the right on the left, and direction of the force is to the left on the right side. So finally, this one concerns. So this part cancels in the difference in the net force. So net force is finally net force applied to this cylinder containing the air molecules is just the change in pressure between this point x and this point x plus dx, change in pressure, and multiplied by the cross-sectional area to make the dimension of force. All right. As a result, the force is a mass is mass contained in this tiny amount of partition is density, cross-sectional area, and thickness dx, right? So mass times this force should be expressed as a mass times acceleration. Force is expressed as a product of mass times acceleration. So acceleration is a force divided by the tiny mass of these air molecules. And acceleration is the time derivative of velocity. Velocity here, the air flow. All right. As a result, force is using this formula. Force is replaced with the cross-sectional area, and change in pressure. We have P, and we have P plus dP on the right side. And then we have the mass term. Mass is this one substituted. And AA cancels, and 1 over rho. Pressure derivative with respect to longitudinal direction x. So we are continuing to, this one is identical to this. We want to find the bulk modulus eventually. Velocity change in here, I have multiplied dt in here. the velocity change. So it becomes a times dt, and velocity change, that's right. So multiply dt here. So this is identical to this, except that I have multiplied dt. And this time scale is, we have thickness dx, and mass flow comes in with the velocity v. So the time is just this distance divided by velocity of this mass flow. They are coming into the plane. All right, so velocity change, it can be computed in terms of this one with the t, and dt dx, this ratio is replaced with the velocity of mass flow. All right, this dx cancels. What we end up with is pressure change divided by density times velocity of massive flow. Now, the change in velocity, there is a v, and this is the v plus dv on the right side. This one we have obtained, and this is coming from the continuity equation. What is continuity equation? This continuity equation, product is always conserved. And then from here, this one is replaced with density divided, actually dv over this velocity change divided by the velocity. And I told you this one is can always express in this way as an identity. This is a steady state continuity equation. Because of that, summarizing everything all together, dv over here, dv equals the dp minus dp rho v squared, okay, rho v squared. So v squared can be expressed as a ratio of this and this. So at the end of the day, what we find is minus pressure change and 1 over v dv, and we have multiplied by 1 over rho. So this one is nothing but the bulk modulus of air molecules. As a result, square root of v squared is the speed of sound, and that one is eventually expressed in terms of the square root of bulk modulus divided by the density of the air. All right, so through this tedious computation, but it is just a straightforward, we end up with the fact that speed of sound is expressed as the square root of bulk modulus divided by the density of the air molecule. All right. Perhaps we can, okay, 14. Consider thin volume. We are keep thinking about cylinder, cross-sectional area A, and the thickness dx of the air in the region x, and x plus dx, with the cross-sectional area of the normal vector n. We consider the fluctuation of the molecules at the longitudinal coordinate. X is the longitudinal coordinate. The wave function represents the displacement of the air molecule from the equilibrium position. the distance between the two leads in the cylindrical region is just simply dx. However, this x and x plus dx is fixed in space, but this psi is the fluctuation of air. As you know, we have a speaker. This speaker face does move. It vibrates. If it doesn't vibrate, it can never create sound. Sound is a propagation of a change in pressure, as that should be generated by the fluctuation of air molecules, like that. Okay, so because of that, this is the default difference in the longitudinal length, but in the sense of air molecule at that point, because they are vibrating a little bit, that is represented by the fluctuation wave function psi. The actual change in as far as the pressure is concerned, this displacement should also be considered. So this is the leading contribution when there is no fluctuation of air molecules. However, there is indeed a contribution coming from the fluctuation of air molecule in this side and this side. And that should be a function of position, because we have reached the steady state. So a little bit abstract, but we have to consider the pure translational effect plus the additional contribution coming from the fluctuation of air molecules. So we call this one is the delta to be the gradient change of this fluctuation multiplied by the displacement by dx. So variation of fluctuation due to the infinitesimal displacement dx. Okay, if there is no air fluctuation, this one disappears, but this one we must consider this contribution. That is the reason. This is closely related to what we have done to compute the bulk modulus. Number 15, a pitch of a sound wave is determined by the frequency. We focus on a traveling sound wave of monochromatic angular frequency omega. Then speed of sound is omega over k, and according to what we have derived, square root of bulk modulus divided by the density. And then according to this wavelength and angular frequency, air molecules vibrates in this kind of form. It is a longitudinal wave oscillating with the wave number and frequency. We can see it is just one absolutely satisfied equation for the wave equation that is propagating along the x-axis. And in here, the wave equation determines the speed of sound as the bulk modulus divided by the density of air molecule. Just what we have computed for the change in the fluctuation of air molecule within the thickness of the dx. that is to be included to find the change. It is a kind of strain. The strain due to the fluctuation of air molecules. So substituting this, the solution for the fluctuation of air molecules along the longitudinal direction, that we can compute the change in pressure from this formula. Okay, change in pressure, because stress over strain is the definition of the bulk modulus. As a result, the change in pressure can be expressed as this one. And we have substituted the solution for the fluctuation d psi that is closely related to the strain. The strain can be computed from the wave function that is for the fluctuation of the longitudinal position of the air molecules. As a result, this bulk modulus, according to our previous calculation for the bulk modulus relation with the air density, volume mass density of air molecules, and the speed of sound, we can substitute those values to find that one. Here, bulk modulus is to be replaced with rho v squared, and the speed of sound is expressed in terms of the ratio of the frequency, angular frequency, and wave number. Finally, you carry out the experiment for disappearing sound due to the complete destructive interference in the KPOPE experiment, and this is the master formula to analyze that experiment. At the end, we consider the beat, and the beat is the interference between two waves with a slight difference in the frequencies. For example, this explicit figure shows the interference between the two sound waves with a slightly different angular frequencies. And red one is the resultant wave. You can see the amplitude is shrinking and enlarging. So up and down, up and down, up and down. This is called the beat. And you can notice the green wave and gray wave. They have a very slight difference in the frequency. This axis is time. So when they make a very tiny difference and repeatedly they disappear at some point that are opposite, here they are making almost complete constructive interference at this point, and destructive interference, constructive interference repeatedly. Anyway, the actual time of beat is our ear noticed this is the period of beat, but mathematically this beat has a period of this amount. This is 2 times the beat. Okay. Although our ear does not distinguish this part and this part that are opposite, the opposite phase, we does notice this one to be the frequency of a beat instead of 2 times. That is mathematical. So blue and brown curves are upper and lower envelopes, blue and brown. We call this big wave shape as an envelope. Beat frequency. Beat frequency is the inverse of a beat period, and that is 1/2. Frequency is a double, and the period is 1/2 of original mathematical formula that has a period of this amount. The reason for the doubling of the beat frequency is that our ears distinguish only the intensity that is proportional to the square of the wave. The magnitude, our ear only notice the magnitude of the sound. Instead, this this one, this on top of this part, this sound, we do not distinguish. So that's the reason why this sound, they our ear notice this one as the period of this beat frequency. Okay, that's it for today.